Okay, so let's look at problem 133, clone graph. So here we would like to practice some of the basic traversal algorithms. So for this problem, we are going to share a breadth first search or depth first search in an iterative fashion. So in order to solve this problem, actually, is just one step further from the classic traversal method. So during this video, I will first go through the statement of the problem, and then we'll look at the idea and the main procedure, and finally we share the code and test the generic case. So given a reference of node in a connected undirected graph, so we are required to return a deep copy or clone of the graph. So below is a class definition. So here is node class. It has two fields. One is value and the other is neighbors. So the graph is given here by an adjacency list representation. So an adjacency list is a collection of unordered lists used to represent a finite graph. So each list describes the set of neighbors of a node in the graph. So that's about the problem. So here is some examples. In example 1, so for example, the return should be the middle one. In the first one, it said that we cannot return the original graph itself. And in the third graph, basically it said that we need to preserve the structure or the topological structure of the original graph. So that's example 1. Example 2 and example 3 are sort of edge cases, I would say. And let's look at the constraints together and analyze them. So the first three are actually routine. The first one is about the number of nodes, and the second one is about the range of the value. Well, the first one is saying that the value field of every node is unique. So the last two actually are going to be important. So it says that there are no repeated edges and no self loops in the graph. So this is actually an important assumption. Basically, the method we are going to share wouldn't cover this case if there are self loops, because we use a set or dictionary to check the nodes that are already visited. So the last one is the graph is connected and all nodes can be visited starting from the given node, meaning that so the graph is a singly connected graph. So otherwise we cannot get the whole graph. So that's about the statement and the constraints of the problem. So now let's look at the method and the idea we are going to use. So here, this is a definition of a node class, which has two fields. One is value and one is neighbors. So the method we are going to use actually is a classic method, as a traversal solution. So we can use breadth first search or depth first search as we like. And the idea here actually is a sort of mapping. So mapping, or more precisely, so the graph and its clone forms a isomorphism. So that's the whole idea. So let me sort of rephrase or emphasize on the key point. So in standard traversal, so one use a set abstract data structure to monitor the nodes that we have already traversed. But here, the extra step is to use dict. It monitors each node visited, and also it can create new nodes, corresponding nodes, at the same time during the procedure. So that's the key. So with that said, we're going to share the code and analyze the code. But before that, so here is a small challenge. So can we try writing a recursive depth first solution? So the solution here we are going to share is a iterative breadth first or depth first solution. So with that said, let's look at the code and the procedures here. So first, I'm going to treat the edge case. So the edge case is that if not node, this case I'm going to return. Why we need to treat this edge case? Because from here we cannot make a map or mapping. So secondly, the generic case. So we want to do some initialization. First is a visited. So this is a dictionary. So in the vanilla traversal algorithm, so we just need to initialize a set, right? So the second one, we're going to, let's first write as queue, because write first search corresponding to queue for the container. Well, depth first search corresponding to a stack. So that's about it. So now let's first do the map. Visited. So I'll map this node to its clone. So how do we get that clone? We just initialize or instantiate a node. Node here. This is the node. So we initialize with the value. So the value going to be the node value. So this is the initialization. So now let's do the actual work, the procedure. So the procedure is basically a standard while loop. So while queue. So then we're going to pop to get the node. So the node is going to be queue pop. So here I'm going to pop from left. So the left corresponding to the height of the queue. So if we pop from the tail, it's going to play a row of stack that's corresponding to depth first search. So here, let's emphasize again. So we are using breadth first search because here we are popping from the height of the queue. So with that said, now let's look at the neighbor of this queue, this node. For neighbor in n neighbors. So neighbors. So what we are going to do is that, so in the vanilla traversal, we are going to include the neighbor if it's not in visited. But here, what we are going to do is that if neighbor not in visited, first we are going to make the map. So visited, that's first this new node or neighbor. So we'll map this to its image. Let's call it. So this value will also be the neighbor node value. So then we do the include operation. So append this new neighbor. So with that said, so after this if block, we are going to do the map like this. So visited the neighbor. So the neighbors append the corresponding image, right? So visited neighbor. So with this done, we're going to return the image. So what we return actually is obvious. It's the image of the node that is visited node, the original node. So with that said, basically that's the code we would like to share. And again, I would like to emphasize the idea. Here, the idea is the mapping method. So the idea of mapping, or in mathematics, it's called isomorphism. So with that said, let's test the cases first. Yeah, this passes the generic case. So let's the example one, not generic case. Let's look at this one. It passes this case. Let's test the example 2. Let's put another one. So again, what we're going to get. So yeah, it also passes this case. So now let's test the generic case. Yeah, it passes the generic case, and yeah, I guess for this problem, so that's about it. So yeah, we're going to practice more about this basic traversal algorithms and its extensions. Thank you very much.